Hello, and welcome again to this third session of the Bayesian Data Analysis course. In this session, we will review the main estimation methods for Bayesian analysis. So I will start with a recap on what is Bayesian inference, and also I will start to cover just from the surface level of the main methods of estimation. Okay. So let's start with a quick recap on what is Bayesian inference. Remember that the Bayesian inference is based on Bayes' rule, that is a method to calculate condition probabilities using the inverse condition probability multiplied by the marginal probability of the second member and divided by the marginal probability of the first member. Therefore, if we apply that to statistical inference, you can have a very desired probability, that is the probability of the parameter being true, given that we have certain data. You can calculate that using the Bayesian inference, that is, use the data likelihood, that is probability of the data being true given that the parameter is true. There you need to multiply it by the prior belief. This is the probability of the parameter being true, and all of that divided by the marginal likelihood, that is the probability of the data being that way. Okay, so now we can have a posterior belief. This is the probability of the parameter being true given the data. And you can calculate that using the data likelihood, the prior belief, and marginal data likelihood. Okay, so with this in mind, now you can assume that the probability changes its meaning. Right now is the expression of the degree of belief on something to occur. And that needs to be expressed mathematically within a probability distribution that is going to be called the prior belief. This prior distribution needs to be specified with great detail, like this is the shape, this is the model, and these are the parameters, okay? So that is going to be combined with data likelihood to obtain a posterior belief, or the distribution of the parameters, the sampling distribution, when the data is now taken into account. Okay, so given that, we have a number of extensions to this inference. For example, prior posterior analysis is basically examining like how was the prior and what changes have been induced in the posterior compared to the prior. For example, changes in form, in position, in variance, in shape, etc. We can also have highest density intervals or credible intervals, that is the main area of the posterior, and we can do things with that. We also can have bias factors that are somewhat like p-values but more informative. And thanks to data ordering invariance, and this is also called Bayesian update, we can do a sequential analysis and robustness analysis. This is the demonstration on how bias factors are more robust to type 1 error inflation than p-values, and therefore we are protected against this problem, and therefore we can do these two things. Sequential analysis is basically introducing new data to create a new inference or new Bayesian inference and see how this changes. You can do that between datasets, for example, original study or replication studies, different studies in different datasets in the same study, meta-analysis, etc. But you can also do that within your own dataset, for example, including row by row, observation by observation, and see how the metric changes. And therefore, you can see the general pattern of how your metric is changing. You can also do robustness analysis, that is here, and it's the same idea, but instead of including new data, you start to change the prior. Normally, you can change the informativeness of the prior, that this is basically the variance parameter of your distribution, but you can tweak anything that you want in the prior. For example, the mean parameter or any other thing. Normally, it's only the variance parameter of the prior, and therefore you can see how a bias factor or any other index that you want changes from very informative priors, normally with very low variance, to very non-informative priors with really high variances and very dispersed. And you can see if there are dramatic changes in your index, or on the contrary, the changes are assumable because they are always in a range. Okay? So with that in mind, I want to start with a cautionary note on bias factors. You can see here in this simulation study that bias factors and p-values can hold a very similar information. As you can see here, the correlation between p-values and bias factors is almost perfect. Therefore, you need to have in mind some things. For example, in the same conditions of non-informativeness, for example, very large priors or normal distributions, etc., p-values are not very different from Bayes factors, because as p-values are reflecting data likelihood, if your prior is not very informative or you don't have any special conditions, Bayes factors can reflect the same information. So we need to be careful on what is distinguishable between Bayes factors and p-values, to not do the same thing just with extra steps or with fancy methods. Okay, so the things that distinguish Bayes factors from p-values are, first of all, the underlying approach to probability, because one is Bayesian and the other one is frequentist. P-values are based on assuming that probabilities are near objects that can be approximated as long as we have bigger samples. And probabilities are a separate object from us, the observers. However, in Bayesian framework, you need to assume that probability is the expression of a belief, the belief on a degree of certainty. Therefore, it becomes subjective. This belief needs to be justified, reported, and also specified, but it's a belief anyway. We are not making any claim on the probabilities by themselves, okay? Because now we assume that they are the expressions of something that is believed. Okay, so this is the first thing, that the number that you get from a Bayes factor or from a p-value means different things. The other thing that distinguishes is that the Bayes factor needs to justify the chosen prior. P-values don't need this, because they just have a bunch of assumptions that you can test, and if everything goes okay, you can just do the test. However, in Bayes factors, you need to just justify which are the priors that you need, and this needs to be justified with rigor. You cannot just do some careless choosing of a prior, okay? And the other thing that distinguishes Bayes factor is that interpretation is, from my point of view, richer, because you can interpret a Bayes factor as a continuous index, a continuous variable, and p-value, it's better not to do that. Why? Because the metric of the p-values, the distribution of the p-values, can be heavily altered if H0 is true or if H0 is false, and also depending on the effect size if the H0 is false. Therefore, it's better not to interpret the p-value as a degree or as the amount of probability of something, because you don't know this metric. Because normally you basically don't know if H0 is true or false, and you don't know the population effect size. Therefore, it is better to just use these thresholds of 0.05, 0.01, etc. However, this is not the case with Bayes factor, because we assume now probabilities are subjective, and therefore arbitrary and specified by the researchers, we benefit from these advantages. Now Bayes factors are a factor and also an odds, and therefore it's a continuous variable. Now we can use that, for example, to express the degree of evidence or supporting H0 and also supporting H1, or on the contrary, if it's inconclusive. You can also contextualize to the field Bayes factors, for example, gathering prior evidence or on other studies of the field, convert them into Bayes factors, for example, and then see if they are very similar, how many points they deviate from each other, and also creating a distribution of Bayes factors and see which is the mean, if your new Bayes factor is far from the majority or not, etc. Operations that you can have when you know that your index reflects a continuous variable, and you can contextualize it to other metrics in the field. You can also contextualize your Bayes factor with other evidence, for example, robustness analysis and also sequential analysis. This is not available with p-values because multiple comparisons are not allowed due to type 1 error inflation. Okay, so final thing is that Bayes factors are just as exposed to bad practice as p-values. Therefore, if you want to perform questionable research practices on a Bayes factor, you can be sure that you can get what you want, as long as data allows this. You can choose to selective reporting, eliminate subjects, add in subjects, or whatever you want. that or also change the prior at convenience of the bias factor, that will happen and will happen easily. So we need to be very careful on that. In addition, it's very sensitive for manipulation to change the prior because of convenience due to changing the bias factor. So you need to be very careful and transparent and rigorous on this way. Okay, so this is like a complement for what I just said, because as you can see here, the relation of bias factors and effect sizes are basically the same, like p-value and effect sizes. Okay, so yeah, there's that. Okay, so as a summary, the Bayesian inference has some pros. For example, now we know the probability of H0 because it's specified as a prior. We don't have assumptions except committing to this prior. Frequentist analysis normally have a bunch of assumptions because they are assuming some sampling distribution properties. Now we specify a specific prior distribution, and therefore if we make a mistake, for example in form, in model, or in parameters, we will have bad results, and we actually can't test that, basically changing the prior. In addition, we have multiple comparisons available, and therefore we can do Bayesian update and see prior sensitivity and sequential analysis or robustness analysis. And also, we can make stopping rules, we can check results, and etc. without making up type 1 error inflation. However, there are some limitations and cautionary notes on Bayesian inference. We need to make an informed and rational decision on the prior. This is not always possible because maybe we are in an exploratory study, and this is not available unless we can have very non-informative priors, and this is basically data likelihood, and that's more or less the same as having a regular p-value from NHHT. In addition, you can bias your conclusions if that data is diverse, or if you have a very informative prior that is not justified enough. For example, there are some critical voices on Bayesianism that advocate that very informative priors can be indistinguishable from data fabrication in Bayesian inference. So there's some debate over this, and that is why you need to be very careful and very rigorous to decide why the prior you're choosing is that prior, especially when you are making informed assumptions or informed priors to a Bayesian inference, which is actually the most powerful thing you can do with Bayes. Okay, the other limitation is that it requires more computation power, because normally analytic methods are not available for getting the posterior, so you need simulation-based solutions, like we will get on that later. Also remind yourself that bias factors and other indices can be very similar to p-values in certain conditions, and also they are not magical or totally protected from bad practice. They are also exposed. Okay, so let's get to Bayesian estimation. Remember, we have priors. We will have priors are probability distributions that you will specify, and therefore they are basically compiled in the computer, so everything is okay. We also have data likelihood, that is also going to be a probability distribution that can be retrieved from data. This can be a little bit difficult, but normally it's no big deal. However, we need the posterior distribution to be obtained, and when we have an analytical method to do that, everything is okay. However, when things become complex, for example, mixed models, generalized linear models, or something like that, it can become tricky from a technical point of view. In addition, in many parts, we need some integration or any other method that we can handle towards getting, for example, highest density intervals. Okay, so if the inference is simple, for example, a t-test or something like that, and normally there's an analytical solution available, and therefore we can use some methods that are very consolidated in Bayesian inference, for example, MAP or EAP and others. Okay, so I will elaborate a little bit on those later. In many occasions, the posterior is not available from an analytical point of view, but we can approximate it by numerical approximations. This is the case of MCMC or Markov chain Monte Carlo methods. Okay. So at that point, when we get the posterior, therefore, the next step is to get its maximum point, because normally we need a point estimate or also an anchor point to create the highest density intervals. And MAP or ERP are very similar to do. So MAP estimation is called maximum a posteriori estimation method, and it's basically a very good method, very robust method to find this maximum point of the posterior distribution as the expected value of the variable of the sampling distribution. Okay, so normally it's equivalent to the mode. You can also have some alternatives like the mean or the median of the posterior. Normally the MAP is a very good way to have this maximum point of the posterior. However, there are problems with MAP estimation in some complex aspects. For example, if the posterior is not integrable, it can be very difficult to make an MAP estimation, or just impossible. Or if we have multimodality, like something like this, the MAP can be trapped in a local maxima, for example, this one, and not being able to get to the real maxima, that is this. And also, if the MAP was able to come to that point, the other group or the other mode would not be informed, and therefore MAP is better not to do, or better not to implement. Okay, these are some readings regarding MAP estimation that you can consult if you want more technical details on how it's done. Also, we have the EAP estimation that is called expected a posteriori, very used in IRT frameworks, and it's very similar to MAP, but it doesn't have full correspondence to the mode, and also it can be more robust in certain complex scenarios. For example, if you have complex datasets that are dichotomous to estimate a latent variable that is continuous or something like that, they are very typical in IRT models, EAP can be a better alternative. However, it can be more complex. So this is just a quick overview on MAP and EAP. I will focus more on MCMC later in the next session.